Now I'd like to introduce a little bit of terminology. We can gain some insight into how a Bode plot will look by taking a look at the form of its transfer function. Let's take a look at a more general transfer function shown here. We'll look at the magnitude of VO over VI. We'll define that as S plus Z1 divided by S plus P1 times S plus P2. Now in general, a transfer function can have any number of components in the top and components in the bottom. Here what I've shown is a transfer function that has a numerator with a single order polynomial and a denominator with a second order polynomial. A little bit of terminology is the components of the numerator, the Zi, are typically referred to as zeros, which is why I've called them Z. And in the denominator, the P sub I are referred to as poles, which is why they are P. If we want to characterize a transfer function, usually people often refer to the order of the transfer function, which is described by the number of poles in the denominator. In this particular example, this would be a transfer function with the second order. Now, in addition to understanding the terminology of transfer functions, it's nice to know what a few typical transfer functions might look like. You've already encountered many of these, but let's just draw them out. For a common system that you already know, and the one we've looked at in most in these lectures, is a low-pass filter. If we were to plot the Bode plot for a low-pass filter, it would have a shape something like this, where this is our frequency, and this is the magnitude of our output over our input. Similarly, we can look at a high-pass filter. Which will have a complementary shape, which looks something like this. And again, this would be the magnitude. Both of these filters are often characterized by their cutoff frequency. So here we have a high cutoff frequency for a low-pass filter. That terminology is a bit confusing. And a low cutoff frequency for a high-pass filter. And something else you might also encounter is the width between the cutoff frequency of a low-pass filter and the DC value is often known as BW, which stands for bandwidth. Two other filters now that you might encounter can be constructed by combining low-pass filters and high-pass filters. One would be a bandpass filter, which would have two cutoff frequencies, such as the one we looked at in the previous example. And another is known as a notch filter, or sometimes a band reject filter. And again, this is the complement. So whereas a band pass filter passes components within a certain frequency range, a notch filter or band reject filter rejects components within a specific frequency range. And again, this would be characterized by two cutoff frequencies. So this is a bit of terminology that I hope you understand now. In looking at the transfer functions, we can characterize them in terms of the number of zeros and the number of poles. And by looking at the number of each, we can get some intuition as to how the transfer function will behave. As we've been doing so far in these series of lectures, we've looked a lot at the extreme cases of DC, or when S or the frequency equals 0, and at very high frequencies when the magnitude of S approaches infinity. And there we can at least get to see if the system we're looking at falls typically into one of these categories. It would be easy to identify something that has low-pass filter characteristics at low frequencies, which could happen for either a notch filter or a low-pass filter, or something which has begins to attenuate at very high frequencies, such as a low-pass filter or a bandpass filter. You can take a look at that by looking at the form of the transfer function and also by characterizing the transfer function experimentally, which is something we'll cover in the next series of lectures.